first thing I want you guys to do is you don't have to write anything down just yet, okay? There's a rough idea here of understanding sine, cosine, tangent. Notice it's asking us for the 6 trig functions. This is not a weird question, right? We've seen this question before. We just haven't seen it in the context of this picture, right? Somebody's asked us for sine, cosine, tangent, cosecant, secant, cotangent of an angle, and we did it all at the beginning, but all from triangles. So the weird thing about this picture is the angle they're referring to is this angle right here. This angle is bigger than 90 degrees, okay, which we could have in a triangle, but can we have an angle bigger than 90 degrees in a right triangle? No, we have like the 90-degree angle. We can't have another one bigger than 90. It'll like make more than 180. It doesn't make sense. So we can't build an actual triangle with the angle that they want us to find these things about. But the only way we know how to find sine, cosine, and tangent is to have the angle in a triangle, right? Okay, so we're kind of in this dilemma. Like, we can't do it with what they've given to us, but we're supposed to. So what we basically say is, you know what? Finding the sine, cosine, or tangent of this angle is really the same as finding the sine, cosine, or tangent of this angle here that's made by that same terminal side on this other side of the x-axis. Okay, so before we get into then exactly how to do that, so that you understand more why that's okay, if they had asked us about like a 30-degree angle, so all this red stuff I'm about to put up here, you don't have to put up here, but it's just to give you a better idea. If they had built an angle, let's say it was 30 degrees, right? And we built a triangle from that with a right angle. If we had some information, we could find the sine, the cosine, and the tangent of the 30 degrees, right? We have an opposite side, we have an adjacent side, we have a hypotenuse, all nicely packaged inside of a little right triangle. Okay? That sine, cosine, and tangent that you would find from that triangle, let me give these some letters. Like say this is x distance, this is y distance, and this is r distance. Now the reason I called them that has to do with the directions that they're on this thing. I called this one x because it's a distance along the x-axis, so I know it's like horizontal. That's like a good name for me because it helps me remember that. I called this distance y because if we're using this coordinate plane, moving vertical is like a y distance. And I called this distance r. Any idea why? Because it's like the radius of the circle. So x, y, and r is kind of arbitrary, but is named really appropriately for the situation. Okay? So notice, like if I wanted to find the sine of 30 in this case, it would be y, because y is the opposite, over r, because r is the hypotenuse. I know there's no numbers in there, but is that okay with everybody? So I put this 30-degree angle here, built a triangle around it, and had some distances here. I could find sine, and then I could go find cosine, tangent, anything else about it. Now let's say they changed it and they didn't want it to be 30. Let's say they made it more like the predicament we were in right here, which is why we're having this whole discussion. Say they took it and made it a really big number that I can't combine with 90 degrees inside of a triangle. So let's say specifically that they made it 150 degrees. Okay? So 150 degrees would end up right here. Okay? But how many degrees are left from where that 150 is marked to get to the 180 mark? 30. So can you see that this triangle, if I built it right here, would actually just be a mirror image of this triangle over here. And I could actually build these same triangles in all different directions. There's another one just like it right here. If I could draw better, right? There's another one just like it over here. There are 4 triangles that are basically the same in every way, except for they just kind of face a different direction on our coordinate plane. Is that okay with everybody? We can see all of those. So there are 4 places where you'd have a 30-degree angle in here. So my argument is this. In all 4 of those triangles, this distance is the same. The thing I called x, right? It's still x. Okay. In all of these. The thing I called y is still y. And the thing I called r is still r. Is that okay with everybody? So all of these triangles have like the same setup. They have x, they have y, they have r. Okay? Every single one of them, x, y, and r. And in every single one of those triangles, if I went to write the sine of 30 degrees, look at what would happen. Y over r, opposite over hypotenuse. Here, y over r, opposite over hypotenuse. Over here, y over r, opposite over hypotenuse. Okay? Over here, y over r, opposite over hypotenuse. It would happen every single time. Okay? So all of these triangles would have the same sine of their angle, whether I was at the 30-degree position or the 150-degree position. The sine of the angle is the same, except for one small detail. Does anybody know what could possibly make the sine, the cosine, or the tangent of these angles different if they have the same x, y, and r everywhere? Think about what you know about a coordinate plane. What is different about this point over here and this point over here? Let's say they're exactly the same distance from the x and y axis.
The x's can be negative if it's on that side, or the y can be negative if it's like over.
Good. Okay, so the numbers aren't going to change, but whether they're negative or positive is going to change because of this whole xy axis deal that's going on right here, right? So over here, the sine is this y over this r. It'll be positive because there's a positive y value and a positive radius. The radius will always be positive because the radius of a circle we wouldn't measure in negative units. Okay? Over here, the sine will also be the exact same thing in this case. Okay? But that's because this point up here and this point up here would literally have the exact same y coordinate if you drew them on a plane. But if I tried to draw the cosine of this angle, the cosine would have been x over r. Here, x would be positive, and so would r. But when I did the cosine of this angle, the x number would be the same, and the r number would be the same, but the x would be negative. Okay? So the reason we can use this angle, even though they are asking us for 150 degrees, and this angle is not 150 degrees, is because 150 just happens to be in a location that's the same as 30, where all the numbers will be the same, but what will change the answers will just be the negatives and the positives. Is this okay with everybody, this idea, before we start actually doing it? So what this means is every time that somebody gives you an angle larger than 90 degrees, so every time that you end up in one of these other quadrants of the circle, you're not going to actually use that angle number when you build a triangle. So I'm not going to actually build a triangle with a 150-degree angle in it. What I'm going to do is I'm going to find that location. I'm going to connect it back to the x-axis. And I'm going to build a triangle that has an angle measure right here, less than 90. Knowing that, I can do the same thing I would do on the other side, and it's all the same except for that this one has a negative x value, a positive y value, and a positive radius. Or this one would have had a positive x value, a positive y value, and a positive radius. Okay? So a reference angle means that, like, when somebody asks me about 150 degrees, sine, cosine, tangent, I do write my answer as like sine of 150 equals, cosine of 150 equals. But I'm not actually using the 150 degree to build the triangle. I'm using its reference angle, which is this angle right here about how far it is from the x-axis. Okay, Jordan? Yes. So it makes sense. Right. Mm-hmm. So what it does for you is it lets you use the same numbers, but like, so right here, let's say we're doing our 30 and our 150, right? So if our 30 is right here, here's where our 150 is marked, but it also builds a triangle that looks just like the one at 30, okay? When we find the cosine of 30 and the cosine of 150, the number part of them is going to look exactly the same. Because whether I'm at a position that's 30 degrees away from my initial side or at a position that's 150 degrees away from the side, these have the same kind of height off of the circle. So they have the same y coordinate. They also have the same distance from this axis, so they also have the same x coordinate, but this one has a positive x coordinate and a positive y coordinate. This one has a negative x coordinate and a positive y coordinate. Okay? So when I go to put them, the number part is going to look the same. Okay? Cosine is adjacent over hypotenuse. And in this case, that's like the x part over the radius. For 30, it's positive because it's a positive x value over a positive radius. At 150, the number part is going to look the same, but what's going to make them different is that at 150, the cosine is actually going to be negative because the x value is going to be negative. So you can use the numbers because it builds a triangle just like it, but they will be different in some respect because of positive and negative around the circle. Okay? So basically, if you know what's happening in just like this one part of the circle, that's the same in every other part of the circle, except for negativity and positivity of certain directions will change. Okay? So when we look at this, and they're asking us over here, what's the sine of theta, the cosine of theta, all this kind of stuff, we basically just want to put it in the context of the x and the y. So here's our theta. It's bigger than 90. That means we would build this triangle right here, and we would use this as our reference angle in here. But we're still technically finding like the sine of 150 or the cosine of 150. It's just that it ended up over here, and you can't build a right triangle with that large angle in there. Okay? So here, this is our x, this is our y, this is our radius. So every time you find the sine of an angle, the angle is always going to be around the middle of the circle. Okay? So the opposite side is always going to be this side over here that has something to do with the y coordinate. And the hypotenuse is always going to be the longest part of the triangle, which in this situation is always going to be the radius of the circle. Okay? So for any sine of any angle, you're always just going to use your y coordinate over your radius. Is that okay? So we're just kind of translating the words opposite over hypotenuse and saying that, yeah, it is opposite over hypotenuse, but if you're in this picture where you have an x and y coordinate plane, the opposite is always the y value and the hypotenuse is always the radius. Okay? So what would the cosine be of any angle? And remember, because all the triangles kind of reflect the same, you can look just at this triangle that we've built here. If this is your angle, okay, and cosine is adjacent over hypotenuse, what variables would you be using? X and r. Okay? So we are always going to use an x coordinate over a radius to state our cosine. And what about our tangent? So look at this angle and think opposite over adjacent. So y over x. And again, I'm not going to memorize these three separately. I'm just going to know which one they're associated with and use their reciprocal. Okay, so that means the cosecant is r over y, the secant is r over x, and the cotangent is x over y. Okay. This means that I don't just need angle measurements. I can find trig functions with angle measurements in a triangle, but I can also now do stuff on the coordinate plane. And when we go through the examples, it'll get more clear what that looks like. Okay. So what we've done is we've just kind of translated sine can be opposite over hypotenuse, but that can also mean on a coordinate plane, y coordinate over radius. Okay? All right. All right, so now if I give you a point, like this problem does, it says, okay, there's a point, 8, negative 15. Find the value of the 6 trig functions. So before that would have been weird to us because a point 8, negative 15 is just a point on the plane. That has nothing to do with trig functions. But now, 8, negative 15 is some point down here in this quadrant. Okay. Remember, what we want to do is we want to build a triangle around that point. We just kind of connect it back with a radius or a hypotenuse. And to build this right triangle, you're always connecting back to the x-axis. Right? If you try to connect to everything else, it won't quite make sense with how we see trig. So we're going to connect it back to the x-axis. Okay? So your right angle should always be touching the x-axis either down here, up here, on this side, or below it. Okay? So I'm going to use this as my reference angle right here. Okay? And then what I want to do is I want to be able to find sine, cosine, and tangent for that angle, so I need some sort of measurements. Okay. Do I know this distance? So 8, because the x-coordinate of the point was 8. Okay. And what's this distance? 15. And we are going to keep the negative with it because remember we talked about those negatives differentiate this angle from the one that's just like it up here, from the one that's just like it over here, and the one that's just like it over here. So the negatives and positives are important now because they're going to make sure we know which quadrant we're in with our triangle. Okay? Now, we don't know the radius or the hypotenuse, but can we figure it out? Yeah, how can we figure it out? Pythagorean theorem. Okay. Does anybody recognize these side lengths? No? Okay, do Pythagorean theorem real quick and tell me what you get. What's that? Not 12. It doesn't matter which one's A and B as long as there's the two sides. As long as the hypotenuse is always the one that's C, then you're fine. Okay? All right, then you guys tell me what you get. Well, it's the same thing as a 3, 4, 5. So it'd be like 9, 12, 15. Because it's just a multiple of all of those. All right, so what do we get here? What did you guys get? 17? Okay. So 8, 15, 17 is actually a famous right triangle, in case you guys forgot. So now to do the trig functions of this, okay. Somebody give me the sine of my angle. Now my angle, okay, is technically all the way around the circle to here, but it's the same thing as if I just use this little reference angle right here. So basically in the triangle we've built, what would the sine be? So you can think opposite over hypotenuse. You can think y-coordinate over radius. What's it going to end up being? So either look at the triangle and find the opposite in the hypotenuse from this right here, or look back at your notes and see that the sine said it could be the y-coordinate over the radius. Ryan? Good. Okay, so negative 15 over 17. And then that also means that like the cosecant is negative 17 over 15. All right, what about the cosine? Somebody else? Okay, so again, that was because that's the opposite over the hypotenuse, just like we knew before. Or with our new definitions, that was the y value over the r value. Okay. Jordan? Good, 8 over 17. So it's our adjacent over our hypotenuse or our x over our r value. Okay, and this means that the secant is 17 over 8. Okay. All right, what about the tangent? Matt? Negative 15 over 8. Okay, so that's the same thing as opposite over adjacent or y value over x value. Okay. And then so the cotangent would take that, and flip it over. Okay. Is that all right with everybody? So once we get the picture, it's the same as what you guys did with the triangle before, just a little different because it's on an x and y axis. Okay. All right, one more thing. Well, I don't want to do this one. All right. Pythagorean theorem. It's like a squared plus b squared equals c squared. So 8 squared plus 15 squared. You should get, when you square 8 and square 15 and add them together, you should get 289. Oh, because of this? Oh, you should be adding. All right. Yes, because once you squared it, it would still be positive. All right. So how do we find exact trig values now in a location? So notice this says the tangent of 300 degrees. So first you need to figure out where is 300 degrees. Okay. So where is 300 degrees? Well, let's see. Okay, okay, good. So these are the quadrants. Okay, so it's down here, right? What is this reference angle we're going to be using in here if we're finding stuff out about this 300-degree angle? So remember, we draw where 300 is, but to make our right triangle, we have to connect it back to the x-axis right here, which means this is our reference angle in here. How many degrees is that angle? So if all the way around to here was 300, how big is this angle right here that's representing from that all the way back around? So 60. So what kind of triangle is this? A 30, 60, 90. So this is kind of weird. They've given us no measurements, but we actually can find the sine, the cosine, the tangent of this triangle. Okay? But we do have to know our 30, 60, 90 pattern. So what is our 30, 60, 90 pattern? What do we put across from the 30? X, okay. What do we put across from the 60? X rad 3. And how do we mark the hypotenuse? 2x. So you might think, like, so we can't find the answers to these. They all have x in them. But when you build a trig ratio and you put one of these sides in a fraction on top of another one of these sides, what's going to happen with the x's? They're going to cancel out, and we're going to be left with a number. So we actually can find the exact value, and x will kind of disappear from them, okay, as we go through this calculation. So we're supposed to find the tangent of 300. That was the directions. So we found where 300 was. We made a little triangle with our reference angle, and then filled in what we know about that kind of triangle. Now that we've got all this information, we want to go back and answer their question. What is the tangent of 300 degrees? So you're looking at your triangle. Okay? You're using this as your reference angle. So tangent uses which part of the triangles? Opposite over adjacent, or y over x. Okay? And so we want to put those together. Now, I've actually forgotten one thing in my labeling. Like, we're only allowed to use this reference angle if we mark the triangle appropriate with positives and negatives. So what did I forget here? Yeah, this side needs to be negative, right? Just because of where it is. Okay. Otherwise, I wouldn't really be finding the tangent of 300. I would really be just finding the tangent of 60, okay, like that this belonged up here somewhere. Okay. All right, so tangent is opposite over adjacent, which is our negative x rad 3 over our adjacent of x, okay, or y over x. These x's will cancel out, and I will be left with negative rad 3. Okay. All right. So the 300 degrees tells us a position. We've now learned that in that position we can build a triangle and fill in the information we know about the triangle. So they give it to us in two forms. They either gave us the point, like in the last example where it was like 8, negative 15, so we actually knew number measurements for the side lengths. Or they give us an angle, but they kind of have to give us a special angle, right? All the angles that they give us right now, like, oh, find cosine of this, tangent of this, but they don't give us any lengths. All of those angles are going to have to work out to be some triangle we already know something about, like this one did, which means it's going to have to be a 30, 60, 90, or what other kind of triangle? A 45, 45, 90, because those are the only ones that we are, like, absolutely sure every time the ratio of the side lengths. Okay? Does that make sense? So the last one, okay, the sine of 3 pi over 4. Again, you have to find where 3 pi over 4 is. If you have to, convert it to degrees. Okay? So I'm going to tell you guys where it is for this time because I want to do the new part of it. So 3 pi over 4 is right here. Okay. So this would be our reference angle. Any idea how big our reference angle is? Anybody kind of used to what pi over 4 represents? 45 degrees. So from 3 pi over 4 to 4 pi over 4 is 1/4, and that was our 45 degrees. So this is 45 degrees, and we're looking at this triangle as our reference. Okay. What is the ratio of sides in a 45, 45, 90? The two things across from the 45s are the same, right? So we'll just call them both x. And what is the hypotenuse? Not 2x, that was in this one. X rad 2, yeah. And this one should be negative in this case. Okay. So now when I go to pick out the sine of this angle, I just look back at my picture. I look at my reference angle that I've built a triangle around, and I go, what is the sine of this angle? So opposite over hypotenuse, okay, or y over r. And in that case, that's x over x rad 2. Again, the x's cancel out. So I get 1 over rad 2. Unfortunately, it's not good enough to leave as it is. So then I end up getting root 2 over 2. Okay. So again, all we did was take kind of like opposite over hypotenuse and translate it into like y over radius. And they're going to give you the information in 2 different forms. Either they're going to give you the angle location, which would completely have to be a 30, 60, 90, or 45, 45, 90 for you to know anything about the side lengths without them telling you a side length. Or they're going to give you an actual point, and then you should know, just like we did with our 8, negative 15, 2 of the side lengths of the triangle. Okay, so for each piece of information, build a triangle there, mark the angle that you're using, and just like before, go back to, okay, sine can be opposite over hypotenuse, cosine can be adjacent over hypotenuse, tangent can be opposite over adjacent, and answer the question you need to answer. Just like you would on the normal coordinate plane. So like this is our x-axis essentially, and this is our y-axis. So this is negative on the x-axis, and this is positive on the y-axis. It's a radius of a circle. So that one has 2 distances involved. So the radius will always be positive, okay? But only the side lengths will change positive or negative, depending positive x, positive y, negative y, okay? Yes, ma'am.
I still don't understand.